Hello, what are we made of? We've come a long way from believing that everything is made of earth, fire, wind, and water. What do we believe now? We believe everything is made out of atoms. But what's our picture of an atom? Balls, basically. Uniform, featureless, boring balls. Until one day, the atom spilled its beans. Those are electrons actually. J.J. Thomson was the dude who first discovered electrons. And J.J. had a revelation. He thought, atoms are plum pudding. If you don't know what a plum pudding is, just think of it as a raisin bun. So in the plum pudding model, electrons are embedded in a positively charged mass, like raisins in a bun. But why positively charged mass? Well, we know the atom is overall neutral in charge, right? So since the electrons are negatively charged, the rest of the atom must be positively charged. Also, we know an atom has mass. Turns out the electrons have very, very tiny mass. So most of the mass is with the rest of the atom. But why a plum pudding? Why not a donut? Maybe there's nothing at the center of the atom? Why not a pretzel? Why do we assume that the rest of the atom, which is a positively charged mass, must be distributed evenly in the atom? To find out the answer, Rutherford has a plan. His approach is summed up by this cartoon. You know, particle physicists have a habit of finding out truths through violence. They always fire stuff at stuff. Remember that when we fired photons at matter, we discovered photoelectric effect? But Rutherford felt that photons are not quite energetic enough. How about electrons? Remember we discovered X-ray when we fired very energetic electrons at matter? We're talking about electrons of a few kilo electron volts. But no, Rutherford wants something even more energetic. So what did Rutherford use to fire at those atoms? Not photons of a few electron volts, not electrons of a few kilo electron volts, but alpha particles of a few mega electron volts. If you don't know, well, alpha particles are very, very energetic helium nuclei, 8,000 times as massive as electrons, and they pack mega electron volts of energy. Now let me show you Rutherford's torture chamber. So right at the center here is a gold foil. Why gold? Was Rutherford trying to show off his wealth? No lah. Rutherford wanted to fire alpha particles at single gold atoms. To do that, he needs something very thin, at most 2 or 3 layers thick of atoms. Gold is very malleable, which makes it the most suitable choice to be the target in Rutherford's scattering experiment. And here is the radioactive source that's going to be emitting those alpha particles. Wrapped around the gold foil is the detector. The detector is coated with some fluorescent material so that when the alpha particles arrive on the detector, you produce a flash, called a scintillation. So what was Rutherford's predictions of the outcome of his experiment? He thought that the thin gold foil should be no match for the very fast alpha particles. So all the alpha particles should be able to pass straight through the gold atoms with no deflection whatsoever. But what is the actual observation? Well, most of the alpha particles, 99% of them, as predicted, went straight through. 99%. That means 1% didn't, right? So it was observed that some alpha particles did suffer some deflection, like this, or like this. There were even a few, very few, 1 in 8,000, which actually got scattered backward, like this. Holy mama, juicy banana. Rutherford was stunned like vegetables. He famously said, "It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Wow, so drama, huh? Now, to understand why Rutherford was so stunned, you have to understand that Rutherford has thought very deeply through what the interaction between alpha particles and the gold atom should be like. Alpha particles are actually helium nuclei. They are 8,000 times more massive compared to electrons. So as the alpha particles approach the atom, the electrons in the atoms are as good as like not there. Kind of like throwing an 8 kilogram bowling ball at 1 gram ping pong balls. So let's ignore the electrons and focus on what's left, which is the positively charged mass. What kind of resistance can the rest of the atom put up against these alpha particles? So we have to ask how strong a repulsive force the alpha particles will experience as they approach the atom. Why repulsive? Because alpha particles are positively charged, and the rest of the atom is also positively charged. Now let me ask you a question. As the alpha particles approach, at which point do they experience the strongest electrical repulsion force? So as they approach the atom, or even travel through the atom, at which point is the electrical repulsion force the strongest? It's actually here, not at the center. It should be here. Are you surprised? If you think of the atom as a point charge, then the electric field strength is given by the formula kq over r squared, right? So many students will think that the force is the strongest at the center, where the electric field strength approach infinity. But the atom is not a point charge. In fact, in the plum pudding model, we assume that the charge is distributed evenly throughout the atom. So it's only when you're outside that all the positive charges are pushing the alpha particles away. Once the alpha particle enters the atom, the field strength starts to decrease already. Because once you enter the atom, this part of the atom behind you will actually be pushing you rightward. And in fact, right at the center of the atom, the field strength is 0. So the actual field strength of the atom looks like this. It increases, reaches a maximum right at the boundary, and then starts to decrease. We can do the calculations. The maximum electrical repulsion force experienced by the alpha particles is this amount here. This is just kqq over r squared, yeah? Charge of the gold atom, charge of the alpha particles. And this number, 10 to the power of negative 10 meters, is the known size of the atom. So it's not a very strong force, yeah? 10 to the power of negative 6. So if the repulsive force is so weak, the alpha particles should pass straight through with no meaningful deflection at all. But we know that the experimental results show that some alpha particles did experience very strong repulsive force. That suggests that our belief that the positively charged mass is uniformly distributed may be wrong. So maybe instead of being uniformly distributed, the positive charges could be concentrated into a tiny ball in the middle of the atom. So as the alpha particles approach, you experience a stronger and stronger repulsive force, and because you can all the way until you are even just 10 to the power of negative 15 meters away from the center of the atom. Now, where did this number come from? Rutherford did some calculations. He realized that for that kind of deflections shown in the experiment, a force as large as 10 to the power of 4 newtons is required. So he kind of worked backwards to figure out how concentrated those positive charges has to be. So Rutherford suggests that maybe all the positive charges are not evenly distributed, but instead they are squeezed into a tiny volume at the center of the atom. He called this thing the nucleus. Only when the positive charges are so concentrated can they produce an electric field so intense that even the mighty alpha particles have to make a U-turn. So there's a nice applet here. If the atom is a plum pudding, then alpha particles should be able to pass straight through them with no meaningful deflection. This is because the positive charges are spread so thin, right? They cannot put up any meaningful resistance. Only if the positive charges are very concentrated at the middle of the atom can we explain the observations from the Rutherford's scattering experiment. So most of the alpha particles will still be able to travel straight through the gold foil, but those that happen to pass quite close to the nucleus, which are those shown in this applet here, yeah, these are the ones that suffer the deflection. Okay, let's now take a little time to appreciate how tiny the nucleus is. We thought something that is 10 to the power of negative 10 meters turns out to be just 10 to the power of negative 15 meters. We overestimated the nucleus size by a power of 5. We were wrong by 100,000 times. But 10 to the power of negative 15 meters is too small, right? It's hard to imagine this tiny length. So why not we put everything into perspective? If we replace the nucleus with the booger, do you know what is the booger? It's what we call psi, yeah? I don't know about yours, but I think mine is about 1 mm across. So 1 millimeter, yeah? So if my booger is the size of the nucleus, then the atom will be 100 meters across. So something that you thought is the size of 100 meters by 100 meters by 100 meters turns out to be the size of your booger. Because of this, do you realize that the nucleus is very, very dense? It's probably the densest thing in the universe that we know, besides a black hole maybe. In fact, if our booger has the same density as the nucleus, it will have a mass of 200 million kilograms. Also, do you realize that most of the atom is just empty space? Take for example this guy here. Say we are looking at 2 meters by 0.5 meters across. He's made of atoms, right? But if we are able to remove all the empty space in him, collect only the nucleus and pack them together, how big a volume would this guy occupy? 20 micrometer by 0.5 micrometer. So all of us is actually 99.999999999% vacuum. Perhaps that's why some people find their life so empty. Alright, that's all. Ta-ta!